The forging process using Chicago's giant steam hammer begins with heating a large billet to a bright orange temperature in a large furnace. Once heated, the glowing billet is transported by overhead crane and placed precisely into the bottom mold of the steam hammer anvil block. The hammer, a towering single-frame double-acting steam unit, uses high-pressure steam to drive a heavy strike bar down with tremendous force. With each controlled blow, the strike bar compresses and shapes the metal. The power of the steam is used to lift the strike bar and press it down, delivering a deadly blow with maximum impact force. The hammer operator closely monitors the forging process, continuously spraying water into the billet, adjusting a valve system to regulate the speed and force of each blow. Rapid blows refine the shape, while a steam cushion relieves internal stresses. Sparks and flakes fly off the billet with each blow as the billet is rotated and repositioned to ensure even deformation. Huge amounts of energy shake the ground with each blow, even as the wooden beams underneath absorb some of the impact. As the forging process progresses, the beak elongates and takes on its final shape. Finally, the forged part is lifted from the anvil, polished and reshaped, ready for controlled cooling and post-forging operations. Workers heat metal billets, position them under the 18T hydraulic forging hammer, and repeatedly strike to shape turbine blades. After multiple controlled blows, the forged blades are cooled and removed for further processing. At the Ruji Spiral Steel Pipe Factory, production starts with storing large metal coils. These coils are then unwound and passed through roller flattening equipment to straighten the material. After flattening, the steel tape is inspected to ensure surface quality and dimensional accuracy. The ends of the tape are cropped to remove defects and enable clean joining. The cropped ends are then butt welded to create a continuous strip suitable for forming. Next, the strip enters a loop storage area, where it is held to ensure smooth and continuous feeding into the forming process. The edges of the strip are cut precisely to ensure a proper weld joint. Before welding, the edges are prepared, and then outside welding is performed as the strip is spirally formed into a pipe. Inside welding follows immediately after the pipe takes shape. Both welds are then cleaned thoroughly to remove slag and impurities. A TV inspection checks the internal weld seam's appearance, followed by continuous ultrasonic testing to detect flaws. If any defects are found, mending is performed. X-ray inspection and shooting checks are also carried out, along with a manual ultrasonic review. Finally, both ends of the pipe are cropped and beveled to prepare for subsequent testing and finishing. The forging process of jet engine blades begins with preforming operations such as extrusion, heading, and upsetting using the USB forging press. This machine combines mechanical speed with hydraulic advantages to reduce setup time, shorten the forging cycle, eliminate intermediate steps, improve blade quality, and boost productivity through automation. The WFL M50 mill turn in Munich showcases a high-performance, multifunctional machining center designed for one-hit processing of complex chuck and shaft parts up to 670 millimeters in diameter. It integrates turning, milling, drilling, hobbing, shaping, and gun drilling under any tool angle, with up to 5-axis interpolation. Featuring wide guideways, long tool pickup magazine, B- and 4-axis turning, and precise in-process measurement, the machine ensures high accuracy and flexibility. With ergonomic design, large safety windows, movable control panel, and easy maintenance access, the M50 delivers efficiency, safety, and operator comfort in advanced manufacturing. The turbine blade is machined in the M50 GMILLTURN using complete 5-axis machining in a single setup, starting from a raw workpiece. Helical spiral and longitudinal milling shape the complex blade profiles, while turning, drilling, and shaping are performed with synchronized spindle operation to maintain precision. Ultra-high-pressure coolant enhances chip evacuation, especially for difficult materials like superalloys. Tool changes are automated via the pickup magazine, and process stability is ensured through integrated monitoring. Final inspection is performed by an in-machine measuring probe, guaranteeing dimensional accuracy of the blade. The machining process of extra-large turbine blades using the CB Ferrari N series begins with the precise alignment and secure clamping of the raw blade workpiece. This is achieved by positioning the blade between two generously sized dividing heads, which serve as the primary clamping and indexing mechanism. These dividing heads are capable of handling blades up to 2.6 meters in length, and thanks to their robust construction, they provide exceptional stability throughout the entire machining cycle. As a result, the setup allows for full 5-axis interpolation and unrestricted access to complex blade geometries. Once the blade is properly clamped, the process proceeds with roughing operations. At this stage, high-torque electrospindles begin removing large volumes of material from the blade's surface using coarse milling cutters. The electrospindles, developed specifically by CB Ferrari, generate significant torque and maintain high feed rates even under heavy cutting conditions. Consequently, the machine achieves outstanding material removal rates while maintaining dimensional control. Simultaneously, high-pressure coolant is directed at the cutting zone to evacuate chips effectively, ensuring that the blade surface remains clean and preventing the risk of tool damage due to chip recutting. As the roughing phase progresses and the blade profile becomes more defined, the newly developed middle support system is introduced. This support is automatically positioned beneath the central span of the blade, precisely where deflection is most likely to occur. Because turbine blades are long and often slender, especially toward the tip, vibrations and chatter could compromise surface finish and dimensional accuracy. Therefore, the middle support is crucial in stabilizing the part during both aggressive and delicate machining operations. It ensures that even the most intricate features can be machined without distortion. Following the stabilization of the blade, the process transitions to semi-finishing and finishing passes. Here, the machine begins contouring the complex pressure and suction surfaces of the blade using smaller, more precise tools. Thanks to the flexible dividing heads, the blade can be continuously indexed and rotated to maintain the optimal tool orientation for each section. Furthermore, the fully stress-relieved cast iron structure of the N-series machine guarantees exceptional vibration damping and thermal stability. This rigid foundation plays a critical role in ensuring unsurpassed accuracy and repeatability, particularly during high-speed 5-axis machining operations. At this point in the process, the machine's adjustable center distance becomes essential. By fine-tuning the space between the opposing spindles and supports, operators can adapt the setup to the specific curvature and geometry of the blade being machined. As a result, tool reach is optimized, cutting forces are minimized, and tool engagement is maximized, especially in areas where the blade curves or twists. This level of flexibility is vital for maintaining consistent cutting conditions and high surface quality across the entire blade length. Meanwhile, chip management continues to be a major focus. With the aid of powerful coolant jets and the integrated chip evacuation design of the electro spindles, chips are continuously removed from the cutting area. This prevents chip accumulation in tight areas such as pockets and root fillets, which could otherwise lead to surface damage or dimensional inconsistencies. Notably, this effective chip evacuation system contributes to uninterrupted machining and extended tool life, even during long cycles. After the blade's main surfaces have been machined, attention turns to more detailed features such as root and tip profiling. These regions often present the most geometrically demanding challenges due to small radii, complex angles, and tight tolerances. Consequently, the dividing heads index the blade to expose the necessary angles, allowing the spindles to reach the root fillets and trailing edges. Specialized tools, such as ball nose and tapered end mills, are employed to finish these areas with high precision. During this process, the middle support remains in position to prevent any unwanted deflection or vibration that could affect tool performance or surface finish. Once the root and trailing edge are machined, the blade tip is addressed. This zone typically requires the most delicate machining operations due to its reduced thickness and aerodynamic shape. Therefore, the process involves ultra-fine finishing passes using ceramic or diamond-coated tools under high spindle speeds and minimal feed rates. At this stage, accuracy and surface integrity are of utmost importance, as even minor deviations could impact the blade's aerodynamic efficiency. To maintain optimal cutting conditions, the support structure remains fully engaged, and coolant continues to flush away fine chips and debris. Following these precise machining operations, the process incorporates in-process measurement and verification. A probing system mounted on the spindle is used to scan the blade's critical areas, capturing real-time geometric data. These measurements are then compared against the target specifications, and any deviations are automatically corrected through toolpath compensation. This closed-loop verification not only guarantees that the blade meets the required tolerances, but also reduces the need for downstream inspection and manual correction. Upon completion of verification, the process moves to the final finishing phase. At this point, ultrafine polishing passes are performed using diamond or carbide tools under minimal depth of cut and extremely slow feed rates. These passes are designed not for dimensional change, but to enhance the surface finish and aerodynamic properties of the blade. As a result, the blade achieves a uniform, mirror-like surface that meets both functional and visual standards. Despite the low material removal rate, the high-speed electro spindles continue to operate with absolute precision, ensuring flawless results. Once all machining and finishing operations are complete, the machine begins the unloading sequence. The middle support system is fully retracted, and the dividing heads release the blade gently. The finished blade is then removed from the machine for final quality control or assembly. Thanks to the high repeatability of the N series, identical results can be achieved across multiple parts, meeting the demands of modern turbine manufacturers. Overall, the entire process from initial clamping to final unloading is defined by precision, efficiency, and adaptability. By integrating advanced features such as the high-torque electro spindles, dynamic dividing heads, newly developed middle support, adjustable center distance, and a rigid machine base, the N series sets a new benchmark in large-scale turbine blade machining. Each component of the system contributes to a stable, high-speed, and highly accurate machining environment, capable of producing the most complex blade profiles required by the modern energy and aerospace sectors. Moreover, this level of integration allows the N series to meet evolving market demands, where both complexity and size are increasing. The ability to process such large and demanding profiles without compromising on speed or accuracy demonstrates not only the robustness of the machine, but also the sophistication of the overall process strategy. Whether machining a single prototype or running high-volume production, the CB Ferrari N530 and its N-series counterparts ensure that every turbine blade is manufactured to the highest standards of quality, precision, and performance. The turbine blade is milled using advanced 5-axis operations. First, the solid carbide end mill 2655T removes bulk material. Then, the barrel shape cutter 3538L refines the surface. Next, the ball nose mill 2834A ensures precision on curved areas. This combination results in around 50% time savings and significantly improved surface quality throughout the machining process. The polishing and finishing process of compressor turbine blades is carried out using a German-made SPE-type CNC polishing machine from IMM. After milling, blades with a surface roughness of raw 1.6 micrometers are mounted onto standard fixtures. The 6-axis SPE machine performs a single polishing cycle using abrasive belts, reducing roughness to raw 0.5 micrometers while maintaining tight tolerances. The machine ensures precise leading and trailing edge contours and consistent surface quality. It accommodates various blade shapes and sizes with interchangeable tooling. The entire process is CNC controlled for high repeatability and stable quality. For example, polishing a 7EA Stage 2 rotor blade from raw 1.4 micrometers to raw 0.5 micrometers takes just 11 minutes. The robotic system polishes turbine blades by removing material in controlled amounts, shaping the fillet radius, platform, and foil. Then, adaptive profiling adjusts the leading edge, trailing edge, and chord length within plus or minus 37.5 microns. The process ends with automated final inspection. The Willemin-Macodel 408MT begins by machining bar stock up to E36 millimeters using a swiveling powered spindle mounted on a B-axis with minus 15 degrees to plus 100 degrees movement. High-speed milling operations are performed up to 42,000 revolutions per minute, with the spindle accelerating from 0 to 30,000 revolutions per minute in just 0.8 seconds. Simultaneously, turning is executed on the A-axis at speeds up to 6,000 revolutions per minute. The machine enables rapid tool changes in 0.8 seconds and precise B-axis indexing in 0.2 seconds. Backface machining is completed using a U-axis rotary unit with a clamping vise. The damaged turbine blade is first secured on a 5-axis milling machine. Initial machining removes material from the affected area. The tool is then automatically changed to a cladding head, which docks with a manifold to prepare for deposition. Laser cladding is applied to the worn surface, adding new material in a controlled manner. After approximately 2 minutes, the system switches to a probing tool to scan the restored surfaces. The collected data is used to guide the next step, blend machining, which ensures a smooth transition between the newly deposited material and the original blade surface. Finally, a polishing tool is used to achieve the desired surface finish. Each operation is precisely controlled to restore the blade's geometry and functionality. GH Induction specializes in the hardening and tempering of driveline components, particularly fixed and plunging joints. The process begins with precise loading of the components into automated induction heating machines. These systems generate high-frequency electromagnetic fields, rapidly heating the metal surfaces to the desired hardening temperature. Once heated, components are immediately quenched with a controlled spray system to achieve optimal hardness and wear resistance. After hardening, tempering is carried out to reduce brittleness while maintaining strength. Components are reheated at lower temperatures in a carefully regulated process to relieve internal stresses and improve mechanical performance. Throughout the entire process, GH's machines ensure precise control of heating parameters, energy efficiency, and repeatability. Thanks to decades of expertise and continuous technological development, GH Induction plays a leading role in the global automotive industry. Today, more than 30% of vehicles worldwide incorporate driveline parts treated by GH's systems. This widespread application confirms GH's commitment to quality, durability, and performance in advanced induction heat treatment. The Mobile Automatic Sander 800 performs fully automated sanding of wind turbine blades with high precision and speed. After navigating into position, the robot begins sanding along the blade's surface, ensuring consistent contact and even pressure. Its advanced automation enables uniform treatment over the entire blade length, while built-in suction efficiently removes dust during the process. The system's high mobility allows it to operate on standard industrial floors. It is easily programmable and adapts to different blade shapes and sizes. This streamlined process significantly reduces sanding time by 50% to 90%, delivering high-quality surface preparation before painting, while enhancing blade durability and performance. Laser hard-facing of low-pressure turbine blades is performed using automated robotic arms to ensure precision. First, the blade surfaces are cleaned and clamped securely in position. Next, a high-powered laser melts a protective coating material typically containing aluminide or silicon chromium alloys onto worn or high-stress zones of the blade. The laser beam precisely follows programmed paths, creating a uniform layer with minimal dilution and distortion. During the process, inert shielding gas prevents oxidation. The system dynamically adjusts laser power and feed rate to suit complex geometries. Finally, the hard-faced blades are cooled and inspected to verify coating quality and adhesion. This method extends service life and enhances resistance to oxidation, corrosion, and high-temperature wear. The robotic blade weld blending process begins with the robot precisely locating the repaired blade tip. Using automated grinding tools, it smooths the weld seam and blends it into the base material. The robot follows the blade's contours to ensure uniform surface quality, removing excess material and creating a seamless finish that meets strict industry standards. The repair process of the steam turbine begins with the removal of the turbine casing, using an overhead crane. All auxiliary pipes and components are disconnected. Next, the upper casing is lifted to expose the rotor and internal parts. The rotor is carefully removed and transported to a separate inspection area. Technicians dismantle the bearings and inspect the rotor blades in journals. Damaged blades are replaced or repaired. The stator components are also cleaned and examined for cracks or corrosion. Once cleaned, the rotor is rebalanced using a dynamic balancing machine. Bearing shells are replaced or refurbished. After inspection and maintenance of all critical parts, the turbine is reassembled, the lower casing is aligned, and the rotor is reinstalled. The upper casing is then placed back and secured with bolts. All pipes and systems are reconnected. Finally, alignment and clearance checks are performed. The turbine undergoes a test rotation followed by operational checks to ensure performance and safety before returning to service. The entire process is executed with precision and coordination to minimize downtime. The assembly includes compressor installation, combustor fitting, turbine integration, and testing at 1600 K exhaust. The RPD-35 from Built Robotics is an autonomous system that automates layout, pile distribution, and driving to streamline solar farm construction. The automated UT inspection system begins with the robo-scanner positioned under the penstock at the 6 o'clock position. Powered by a portable generator, the system scans downhill first, inspecting the internal surface for ID corrosion and evaluating the integrity of long seam welds. The operator monitors the progress using a dedicated data system. As the scanner approaches the pipe's lower end, it continues scanning under the pipe before exiting from underneath. Then, the scanner transitions to scanning uphill, adjusting its position to follow the steep and rugged terrain. Additional uphill scanning is performed to ensure full coverage. The system moves around the pipe, adapting to various angles and elevations. Finally, the RoboScanner configures itself specifically for long seam inspection, performing precise evaluations of the welds along the entire pipe length. This ensures both corrosion detection and seam integrity are thoroughly assessed throughout the inspection process. The robotic wind turbine inspection process begins by placing an autonomous robot on the surface of a multi-million euro turbine blade. Designed with lightweight materials and an anti-slip structure, the robot can operate reliably despite strong side gusts or vibrations from the wind turbine blade. It uses industrial-grade vacuum cups for secure adhesion and high-power density DC motors, combined with high-performance pneumatics, to ensure stable and precise movement along the blade surface. The control system is engineered to handle worst-case failure scenarios safely. With simultaneous inspection capabilities on both sides of the blade spar, the robot performs comprehensive evaluations without repositioning. Its navigation system allows consistent movement and accurate data collection, even on curved surfaces. This advanced robotic system enables fatigue life assessment of wind turbine blades in less than 4 hours, offering a fast, reliable, and automated solution to structural health monitoring in harsh and dynamic environments.